LangChain is a framework for developing applications powered by language model. It enables applications that are context-aware and applications that reason. By context-aware, we mean the fact that we can connect a language model to sources of context, such as prompt instructions, few-shot examples, and content to ground its response in. By applications that reason, we refer to the fact that we rely on a language model about how to answer based on the provided context, or to reason what actions it should take. The LangChain framework consists of several parts: LangChain libraries, LangChain template, LangServe, and LangSmith. LangChain libraries are Python and JavaScript libraries that contain interfaces and integrations for a myriad of components, a basic runtime for combining these components into chain and agents, and off-the-shelf implementations of chains and agents. LangChain templates, on the other hand, provide a collection of easy deployable reference architectures for a wide variety of tasks. LangServe is a library for deploying LangChain chains as a REST API, and LangSmith is a developer platform that lets you debug, test, evaluate, and monitor chains built on any LLM framework and seamlessly integrate with LangChain. These products, LangSmith, LangServe, LangChain template, and LangChain libraries, simplify the entire application lifecycle. For development, you can write your applications in LangChain or LangChain.js and hit the ground running using templates for reference. When you want to productionize, you can use LangSmith to inspect, test, and monitor your chain so that you can constantly improve and deploy with confidence. For deployment, you can turn any chain into an API with LangServe. Regarding LangChain library, the main value proposition of the LangChain packages are components and off-the-shelf chains. Components are composable tools and integrations for working with language model. Components are modular and are easy to use, whether you're using the rest of the LangChain framework or not. Off-the-shelf chains are built-in assemblages of components for accomplishing higher-level tasks. Off-the-shelf chains make it easy to get started. Components make it easy to customize existing chains and build new ones. The LangChain libraries themselves are made up of several different packages: LangChain Core, LangChain Community, and LangChain. LangChain Core contains base abstractions and LangChain expression language. LangChain Community contains third-party integration, and LangChain itself contains chains, agents, and retrieval strategies that make up an application's cognitive architecture. The LangChain expression language, or LCEL, is a declarative way to compose chains. The LangChain expression language was designed from day one to support putting prototypes in production, with no code changes from the simplest prompt plus LLM chain to the most complex chain. The LangChain expression language provides several features that you might find useful in your LangChain application, such as streaming support. For example, when you want to build your chains with LangChain expression language, you get the best possible time to first token. That is the time elapsed until the first chunk of output comes out. For some chains, this means, for example, we stream tokens straight from an LLM to a streaming output parser, and you get back parsed incremental chunks of output at the same rate as the LLM provider outputs the raw token. Another feature of the LangChain expression language is the sync support. That is, any chain built with the LangChain expression language can be called both with the synchronous API, for example in your Jupyter notebook while prototyping, as well as with the asynchronous API, for example in a LangServe server. This enables using the same code for prototypes and in production with great performance and the ability to handle many concurrent requests in the same server. Another feature of the LangChain expression language is the optimized parallel execution. Whenever your LangChain expression language chains have steps that can be executed in parallel, for example if you fetch documents from multiple retrievers, we automatically do it both in the sync and the async interface for the smallest possible latency. The LangChain expression language also offers support for retries and fallbacks. That is, for example, you can configure retries and fallbacks for any part of your LangChain expression language chain. This is a great way to make your chains more reliable at scale. We're currently working on adding streaming support for retries and fallbacks, so you can get the added reliability without any latency cost. For more complex chains, it's also often very useful to access the result of intermediate steps even before the final output is produced. This can be useful to let end users know something is happening, or even just to debug your chain. You can stream intermediate results, and it's available on every LangServe server. The input and output schemas give every LangChain expression language chain pedantic and JSON schemas inferred from the structure of your chain. This can be used for validation of input and outputs and is an integral part of LangServe. The LangChain expression language also offers seamless LangSmith tracing integration. So as your chains get more and more complex, it becomes increasingly important to understand what exactly is happening at every step. With the LangChain expression language, all steps are automatically logged to LangSmith for maximum observability and debuggability. Finally, another feature of the LangChain expression language is the seamless LangServe deployment integration. So any chain created with the LangChain expression language can be easily deployed using LangServe. Regarding the LangChain expression language interface, the LangChain expression language interface makes it easy to create custom chains with the help of the Runnable protocol. The Runnable protocol is implemented for most components. This is a standard interface which makes it easy to define custom chains as well as invoke them in a standard way. The standard interface includes stream, invoke, and batch. Stream is used to stream back chunks of the response. Invoke is used to call the chain on an input, and batch is used to call the chain on a list of inputs. Apart from the standard interface, we also have the corresponding async methods. Those are a stream, a invoke, a batch, and a stream_log. A stream is used to stream back chunks of the response in an asynchronous fashion, function invoke is used to call the chain on an input async, and batch is used to call the chain on a list of input async. Finally, stream_log is used to stream back intermediate steps as they happen, in addition to the final response. The input and the output varies by component. So for example, for the prompt component, the input can be a dictionary and the output can be a prompt value. For the chat model component, the input can be a string, a list of chat messages, or a prompt value, and the output is a chat message. For the LLM component, the input can be a string, a list of chat messages, or a prompt value, and the output is a string. For the output parser component, the input type is the output of an LLM or a chat model, and the output type depends on the parser. For the retriever component, the input type is a single string, while the output type is a list of documents. For the tool component, the input is a single string or a dictionary depending on the tool, while the output type depends on the tool. All runnables expose input and output schemas to inspect the inputs and output. The input schema being an input pydantic model auto-generated from the structure of the runnable. The output schema is an output pydantic model auto-generated from the structure of the runnable. If we take a look at this method, we can create a simple prompt template plus chat model. For this, we import the chat open API and the chat prompt template. We instantiate the model as well as the prompt using the prompt template method and providing a string containing the text "tell me a joke about curly braces" topic. And then we define our chain as simply prompt vertical bar model. Finally, LangChain also provides a series of standard extensible interfaces and integrations for the following module: the model I/O module, the retrieval module, and the agents module. The model I/O deals with the interface with language models. The retrieval module deals with the interface with application-specific data, and the agents module deals with letting models choose which tools to use given high-level direction. Regarding the model I/O module, the core element of any language model application is the model itself. LangChain gives you the building block to interface with any language model, and it does this through prompts, chat models, LLM, and output. With prompts, you can templatize and dynamically select as well as manage model inputs. With chat models that are backed by a language model but take a list of chat messages as input and return a chat message. By chat models, we mean models that are backed by a language model that take a list of chat messages as input and return a chat message. By LLMs, we mean models that take a text string as input and return a text string. With output parsers, we can extract information from model outputs. It's important to know the distinction between LLMs and chat models. LLMs and chat models are subtly but importantly different. LLMs in LangChain refer to pure text completion model. The APIs they wrap take a string prompt as input and output a string completion. OpenAI's GPT-3 is implemented as an LLM. Chat models are often backed by LLM, but tuned specifically for having conversation. And crucially, their provider APIs use a different interface than pure text completion model. Instead of a single string, they take a list of chat messages as input. Usually, these messages are labeled with the speaker, usually one of a system, AI, and human options, and they return an AI chat message as output. GPT-4 and Anthropic's Claude 2 are both implemented as chat models. Regarding the retrieval module, many LLM applications require user-specific data that is not part of the model's training. The primary way of accomplishing this is through retrieval augmented generation, also known as RAG or RIG. In this process, external data is retrieved and then passed to the LLM when doing the generation step. LangChain provides all the building blocks for RAG application from simple to complex. This section of the documentation covers everything related to the retrieval step. For example, the fetching of the data. Although this sounds simple, it can be subtly complex. This encompasses several key modules: the document loaders, the document transformers, the embeddings, the vector stores, and the retriever. Document loaders load documents from many different sources. LangChain provides over 100 different document loaders, as well as integrations with other major providers in the space, like Airbyte and Unstructured. LangChain provides integrations to load all types of documents, like HTML, PDF, or code, from all types of locations, such as private S3 bucket and public website. Then we have the document transformer. A key part of retrieval is fetching only the relevant parts of documents. This involves several transformation steps to prepare the document for retrieval. One of the primary ones here is splitting or chunking a large document into smaller chunks. LangChain provides several transformation algorithms for doing this, as well as logic optimized for specific documents such as code or markdown. Then we have text embedding models. Another key part of retrieval is creating embeddings for documents. Embeddings capture the semantic meaning of the text, allowing you to quickly and efficiently find other pieces of a text that are similar. LangChain provides integrations with over 25 different embedding providers and methods, from open source to proprietary APIs, allowing you to choose the one best suited for your needs. LangChain provides a standard interface, allowing you to easily switch between models. Then we have vector store. With the rise of embeddings, there has emerged a need for databases to support efficient storage and searching of these embeddings. LangChain provides integrations with over 50 different vector stores, from open source local ones to cloud-hosted proprietary, allowing you to choose the one best suited for your needs. LangChain exposes a standard interface, allowing you to easily swap between these vector stores. Finally, we have the retrieval aspect, which is covered in LangChain by Retriever. Once the data is in the database, you still need to retrieve it. LangChain supports many different retrieval algorithms, and this is one of the places where it adds the most value. LangChain supports basic methods that are easy to get started, namely simple semantic search. However, we also have added a collection of algorithms on top of this to increase performance. These include parent document retriever, which allows you to create multiple embeddings per parent document, allowing you to look up smaller chunks but return a larger context. A self-query retriever, since user questions often contain a reference to something that isn't just semantic but rather expresses some logic that can be best represented as a metadata filter. Self-query allows you to parse out the semantic part of a query from other metadata filters present in that. We also have the ensemble retriever, because sometimes you may want to retrieve documents from multiple different sources or using multiple different algorithms. The ensemble retriever allows you to easily do this. One last aspect regarding retrieval is indexing. The LangChain indexing API syncs your data from any source into a vector, helping you to avoid writing duplicated content, avoid recomputing embedding, all of which should save you time and money, as well as improve your vector search. One last module to cover is the agents module. The core idea of agents is to use a language model, choose a sequence of actions to take. In chain, a sequence of actions that is in code. In agent, a language model is used as a reasoning engine to determine which action to take and in which order. There are several key components here. The agent itself, which is the chain responsible for deciding what step to take next. This is powered by a language model and the prompt. The inputs to this chain are tools, script descriptions of available tools, user input, that is the high-level objective, and finally intermediate step, that is any action or tool input pairs are previously executed in order to achieve the user input. The output is the next action to take or the final response sent to the user. Agent action or agent finish. An action specifies a tool and the input to that tool. Different agents have different prompting styles for reasoning, different ways of encountering inputs, and different ways of parsing the output. Besides the agent, other important components are the tools, the toolkit, and the agent execute. Tools are functions that the agent can invoke. There are two important design considerations around giving the agent access to the right tools and describing the tools in a way that is most helpful to the agent. Without thinking through both, you won't be able to build a working agent. If you don't give the agent access to a correct set of tools, it will never be able to accomplish the objectives you give it. If you don't describe the tools well, the agent won't know how to use them properly. LangChain provides a wide set of built-in tools, but also makes it easy to define your own tools, including custom description. Regarding the toolkit concept, for many common tasks, an agent will need a set of related tools. For this, LangChain provides the concept of toolkits, groups of around 3 to 5 tools needed to accomplish specific objectives. For example, the GitHub toolkit has a tool for searching through GitHub issues, a tool for reading a file, a tool for comment. Finally, the agent executor is a runtime for an agent. This is what actually calls the agent, executes the actions, chooses, passes the actions, outputs back to the agent, and repeat. In pseudocode, it can look roughly like this. While it may seem simple, there are several complexities this runtime handles for you, including handling cases where the agent selects a non-existent tool, handling cases where the tool errors, handling cases where the agent produces output that cannot be parsed into a tool invocation, as well as logging and observability at all levels, to standard output and or to lines.
Now let's go through a quick chart for LangChain, showing you how you can get set up with LangChain, LangSmith, and LangServe, how you can use the most basic and common components of LangChain, such as prompt template, models, and output parsers, how you can use LangChain expression language, the protocol that LangChain is built on, and which facilitate component chaining. We'll also show you how to build a simple application with LangChain, how you can trace your application with LangSmith, and how you can serve your application with LangServe. Let's discuss the setup. First of all, you'll need to install LangChain. You can do so either with pip or with conda. Afterwards, you'll need to set up the environment. Using LangChain will usually require integrations with one or more model providers, data stores, APIs, and so on. For this particular example, we'll use OpenAI's model API. First, we'll need to install their Python package via pip install OpenAI. Accessing the API requires an API key, which you can get by creating an account. Once we have a key, we'll want to set it as an environment variable by running export OpenAPI key equals, and then you'll have to type your particular API. If you'd prefer not to set an environment variable, you can pass the key in directly via the OpenAPI key name parameter when initiating the OpenAI LLM class. In Python, we can do this by importing the chat OpenAI class from LangChain chat model, and then we create our LLM variable by instantiating the chat OpenAI object and passing in our OpenAI API key. Next, we'll need to set up LangSmith. Many of the applications you build with LangChain will contain multiple steps with multiple invocations of LLM calls. As these applications get more and more complex, it becomes crucial to be able to inspect what exactly is going on inside your chain or agent. The best way to do this is with LangSmith. Note that LangSmith is not needed, but it is helpful. If you do want to use LangSmith, after you sign up at the link above, make sure to set up your environment variables to start logging traces. Export, for example, you can export the LangChain tracing v2 variable and set it to true, and you can also export the LangChain API key. Finally, we'll also need to set up LangServe. LangServe helps developers deploy LangChain chains as REST API. You do not need to use LangServe to use LangChain, but in this guide, we'll show how you can deploy your app with LangServe. What you'll need to do is to install LangServe using the pip install LangServe all command. After discussing the setup, now we can look at how you can build with LangChain. LangChain provides many modules that can be used to build language model applications. Modules can be used as standalone in simple applications, and they can be composed for more complex use cases. LangChain composition is powered by LangChain expression language, or LCEL, which defines a unified runnable interface that many modules implement, making it possible to seamlessly chain components. The simplest and most common chain contains 3
things: an LLM or a chat model, a prompt template, and an out parser. Regarding the LLM or the chat model, the language model is the core reasoning engine here. In order to work with LangChain, you need to understand the different types of language models and how to work with them. Regarding the prompt template, this provides instructions to the language model. This controls what the language model outputs, so understanding how to construct prompts and different prompting strategies is crucial. Regarding the output parser, these translate the raw response from the language model to a more workable format, making it easy to use the output downstream. In this guide, we'll cover those three components individually and then go over how to combine them. Understanding this concept will set you up well for being able to use and customize LangChain applications. Most LangChain applications allow you to configure the model and or the prompt, so knowing how to take advantage of this will be a big enabler. There are two types of language models: LLMs and chat models. In the case of LLMs, the underlying model takes a string as input and returns a string. In the case of chat models, the underlying model takes a list of messages as input and returns a message. Strings are simple, but what exactly are messages? The base message interface is defined by base message, which has two required attributes: content and role. Content represents the content of the message, usually a string, and role is the entity from which the base message is coming from. LangChain provides several objects to easily distinguish between different roles: human message, which is a base message coming from a human or user; AI message, which is a base message coming from an AI or an assistant; system message, which is a base message coming from the system; and function message or tool message, which is a base message containing the output of a function or a tool call. If none of these roles sound right, there is also a chat message class where you can specify the role manually. LangChain provides a common interface that's shared by both LLMs and chat models. However, it is useful to understand the difference in order to most effectively construct prompts for a given language model. The simplest way to call an LLM or a chat model is using the invoke method, the universal synchronous call method for all LangChain expression language objects. LLM.invoke takes in a string and returns a string, while chat model.invoke takes in a list of base message and returns a base message. The input types for these methods are actually more general than this, but for simplicity, here we can assume LLM only take strings and chat models only take lists of messages. Let's see how we can work with these different types of models and these different types of input. First, let's import an LLM and a chat model. We can do this by importing the OpenAI class and the chat OpenAI class and instantiating our LLM and chat underscore model variable. LLM and chat model objects are effectively configuration objects. You can initialize them with parameters like temperature and others and pass them around. Then we import the human message class from LangChain schema. We define a text variable and a messages variable, which is a list containing an instantiated human message object to which we pass our text variable. We can then call the invoke method of the LLM with the text variable provided, and we will get a response. We can also call the invoke method of the chat model and we'll get back an AI message. Regarding prompt template, most LLM applications do not pass user input directly into an LLM. Usually they will add the user input to a larger piece of text called a prompt template that provides additional context on the specific task at hand. In the previous example, the text we passed the model contained instructions to generate the company name. For our application, it would be great if the user only had to provide the description of a company or product without worrying about giving the model instructions. Prompt templates help with exactly this. They bundle up all the logic for going from user input into a fully formatted prompt. This can start off very simple. For example, a prompt to produce the above string would just be importing the prompt template class from LangChain prompt, setting up the prompt variable by calling the prompt template method of the prompt template class, and finally calling the format method on the new prompt variable and providing, in this case, the product parameters. However, the advantages of using these over raw string formatting are several. You can partial out variables. For example, you can format only some of the variables at a time. You can compose them together, easily combining different templates into a single prompt. For explanations of these functionalities, prompt templates can also be used to produce a list of messages. In this case, the prompt not only contains information about the content, but also each message, its role, its position in the list, and so on. Here, what happens most often is a chat prompt template is a list of chat message templates. Each chat message template contains instructions for how to format that chat message, its role, and then also its content. Let's take a look at this below. First, we import the chat prompt template class from LangChain prompt chat. Then we initialize our template and human template variable. Then we initialize our chat underscore prompt variable by calling the from messages method of the chat prompt template class, passing in a list with two tuples for the template and the human template. Finally, we call the format messages method of the chat prompt variable with the parameters input language, and the output parsers convert the raw outputs of a language model into a format that can be used downstream. There are a few main types of output parsers, including convert text from LLM into structured information such as JSON, to convert a chat message into just a string, to convert the extra information returned from a call besides the message, like OpenAI function invocation, into a string. In this getting started guide, we will write our own out parser, one that converts a comma separated list into a list. We import the base output parser class from LangChain schema. Then we define the comma separated list output parser, providing the base output parser as a base class, and we use this to parse the output of an LLM call to a comma separated list. We also define the parse method, which takes as parameter self and also a string named text. This will parse the output of an LLM call. We write the logic for parsing the output of the LLM call, and that is our class. Now we can use it by simply instantiating comma-separated list output parser and calling the method part, to which we can pass a comma-separated string and will obtain as output a list of string. In terms of composing with LCEL, we can now combine all of these into one chain. This chain will take input variables, pass those to a prompt template to create the prompt, pass the prompt models to a language model, and then pass the output through an optional output parser. This is a convenient way to bundle up a modular piece of logic. So let's see it in action. From typing, we import the list class. Then we import the chat OpenAI class, the chat prompt template class, and the base output class. We once again have our code that defines the comma-separated list output parser class. Then we define our template and our human template. We define the chat underscore prompt variable by calling the from messages method of the chat prompt template class. Then we define the chain variable as chat underscore prompt vertical bar, then an instance of chat OpenAI, then an instance of comma-separated list output parser. Then we can call the invoke method of the chain variable by passing in a dictionary with the key value pair, text, and colors, and we'll obtain the output as a list of color names. You can note that we are using the vertical bar syntax to join these components together. This vertical bar syntax is powered by the LangChain expression language, LCEL, and relies on the universal runnable interface that all of these objects implement.
Regarding tracing with LangSmith, assuming we've set our environment variable as shown in the beginning, all of the model chain calls we've been making will have been automatically logged to LangSmith. Once there, we can use LangSmith to debug and annotate our application traces, then turn them into datasets for evaluating future iterations of the application. Regarding serving with LangServe, now that we've built an application, we need to service it. LangServe helps developers deploy LCEL chains API as a REST API. The library is integrated with Fast API and uses Pydantic for data value. To create a server for our application, we'll make a serve.py file with three things: the definition of our chain, our Fast API app, and a definition of a route from which to serve the chain, which is done with langserve add route. We first import the list class, the Fast API class from Fast API, the chat prompt template, chat OpenAI, base out parser from LangChain, and the add route method from langserve. Then we move on to the chain definition. We define our comma-separated list output parser class, then we define our template variable, our human template variable, our chat underscore prompt variable, which we obtain by calling the from messages method on the chat prompt template class. Then we define our category underscore chain variable as chat prompt vertical bar, chat OpenAI instance vertical bar, comma-separated list output parser. Then we write our app definition, and we use the Fast API class to instantiate our app object. And finally, we add the chain route by using the add route method, to which we pass our app, our category chain, and the path, in this case category underscore chain. And that's it. We can simply execute the file using Python serve.py, and then we should see our chain being served at localhost 8000. Every LangChain service comes with a simple built-in UI for configuring and invoking the application with streaming output and visibility into intermediate tests. Head to localhost 8000 category chain playground to try it out. To set up a client for programmatically interacting with our service, we can easily do this with the langserve.remote runnable class. Using this, we can interact with the serve chain as if it were running client-side. First, we import the remote runnable class from langserve. We instantiate the remote runnable. We assign to the remote chain variable an instance of the remote runnable class. We call the invoke method on the remote underscore chain variable, passing a key value pair composed of text and colors, and we receive as output a list of colors: red, blue, green, yellow, and orange. In terms of security, LangChain has a large ecosystem of integrations with various external resources like local and remote file systems, APIs, and databases. These integrations allow developers to create versatile applications that combine the power of LLMs with the ability to access, interact with, and manipulate external resources. In terms of best practices, when building such applications, developers should remember to follow good security practices, such as limiting permissions, anticipating potential misuse, and defense in depth. In terms of limiting permissions, scope permissions specifically to the application's needs. Granting broad or excessive permissions can introduce significant security vulnerability. To avoid such vulnerabilities, consider using read-only credentials, disallowing access-sensitive resources, using sandboxing techniques such as running inside a container as appropriate for your application. In terms of anticipating potential misuse, always assume that any system access or credentials may be used in any way allowed by the permissions they are assigned. For example, if a pair of database credentials allows deleting data, it's safest to assume that any LLM able to use those credentials may in fact delete data. In terms of defense in depth, no security technique is perfect. Fine-tuning and good chain design can reduce but not eliminate the odds that a large language model may make a mistake. It's best to combine multiple layered security approaches rather than relying on a single layer of defense to ensure security. For example, use both read-only permissions and sandboxing to ensure that LLMs are only able to access data that is explicitly meant for them to use. Risks of not doing so include but are not limited to data corruption or loss, unauthorized access to confidential information, compromised performance, or availability critical resource. Example scenarios with mitigation strategies: a user may ask an agent with access to the file system to delete files that should not be deleted, or read the content of files that contain sensitive information. Limit
the agent to only use a specific directory and only allow it to read, write files that are safe to read or write. Consider further sandboxing the agent by running it in a container. A user may ask an agent with write permissions to an external API to write malicious data to the API or delete data from the API. To mitigate, give the agent read-only API key or limit it to only use endpoints that are already resistant to such misuse. A user may ask an agent with access to a database to drop a table or mutate the schema. To mitigate, scope the credentials to only the tables that the agent needs to access and consider issuing read-only credentials. If you're building applications that access external resources like file systems, APIs, or databases, consider speaking with your company's security team to determine how to best design and secure your application. When it comes to the LangChain expression language, the most common and valuable composition is taking a prompt template or a chat prompt template, an LLM or a chat model, and an output parser, the so-called prompt plus LLM. Almost any other chains you build will use this building block. Let's see an example with a prompt template and an LLM. The simplest composition is just combining a prompt and a model to create a chain that takes user input, adds it to a prompt, passes it to a model, and returns the raw model out. Note, you can mix and match prompt template, chat prompt template, and LLMs or chat models as you like here. Oftentimes, we want to attach KWR that will be passed to each model call. Here are a few examples of that. For example, attaching stop sequencing or attaching function call information by defining the list function, the chain variable, and calling the method invoke. We can also use the prompt template plus LLM plus out parser combination. We can also add in an output parser to easily transform the raw LLM chat model output into a more workable format. Notice that this now returns a string, which is a much more workable format for downstream tasks. Functions out parser. When you specify the function to return, you may just want to parse that directly. Simplifying input. To make invocation even simpler, we can add a runnable parallel to take care of creating the prompt input for us. Since we're composing our map with another runnable, we can even use some syntactic sugar or just use a dictionary. We can also add in a retrieval step to a prompt and LLM, which adds up to a retrieval augmented generation chain. We first import all our classes, define the vector store, the retriever, the template, prompt, the model, build the chain, and then call the method invoke on the chain. We can also define another template and the prompt, build the chain, and again call the method invoke. For a conversational retrieval chain, we can easily add in conversation history. This primarily means adding in chat message history. Once again, we do our import, we define the underscore template, the condensed question prompt template, and the answer prompt, as well as the default document prompt. We create a method for combining the document, we define the input and the contact, we build the conversational Q&A chain, and we call the method invoke on the conversational Q&A chain to obtain our output. With memory and returning source document, this shows how to use memory with the above. For memory, we need to manage that outside at the memory. For returning the retrieved documents, we just need to pass them through all the way. We do our import, we define the memory, the loaded memory, the standalone question, the retrieved document, the final inputs, the answer, and we build the final chain. We call the method invoke and we obtain the result. We can also use the method save contact on the memory as well as the method load memory variable, and we can see the history output. Once again, we can redefine the input, call the method invoke again, and obtain the new result. Now let's discuss about multiple chains using the LangChain expression language. Runnables can easily be used to string together multiple chains. To do this, we can import item getter from operator. We can also import the classes chat OpenAI, chat prompt template, and str output parser from LangChain. We define prompt 1, what is the city person is from, and prompt 2, what country is the city curly brace city in, respond in curly brace language. Then we define our model, chat OpenAI, object in. Then we build chain 1 from prompt 1, model, and str out parser in. Then we build chain number 2 as a dictionary with the keys city, language, city and language, vertical bar prompt 2, vertical bar model, vertical bar str output parser instant. And then we can invoke chain 2 providing the person Obama and the language Spanish, and we'll obtain our answer in Spanish. We can also import runnable pass-through from LangChain for runnables. We define prompt 1, generate a curly brace attribute color, return the name of the color and nothing else. We also define prompt 2, what is a fruit of color, curly brace color, return the name of the fruit and nothing else. Then we define prompt 3, what is the country with a flag that has the color, curly brace color, return the name of the country and nothing else. Then we define prompt 4, what is the color of the fruit, curly brace fruit, and the flag of country, curly brace country. We build our model parser as model, vertical bar, str output parser. We define the color generator as a dictionary with the key attribute, vertical bar prompt 1, vertical bar dictionary with the key color. We define color to fruit as prompt 2, vertical bar model parser. And we define color to country as prompt 3, vertical bar model parser. Finally, we define the question generator as color generator, vertical bar dictionary with the key value for fruit and country, vertical bar prompt 4. Finally, after we build the question generator, we can call the method invoke by passing the parameter worm, and we'll get a chat prompt value object with the messages, human message with the content, what is the color of a strawberry, and the flag of China, and the example attribute set to false. We can store this in the variable prompt, and then we can call the invoke method on the model itself by passing the prompt variable, and we'll obtain an AI message with the content, the color of an apple is typically red or green, the flag of of China is predominantly red with a large yellow star in the upper left corner and 4 smaller yellow stars surrounding it. Branching and merging. You may want the output of one component to be processed by 2 or more other components. Runnable parallels let you split or fork the chain so multiple components can process the input in parallel. Later, other components can join or merge the results to synthesize a final response. This type of chain creates a computation graph that looks like the following. Input branch 1 and 2, and finally the 2 branches will be joined together in a combined operation. The way this looks like in code is like this. We first define our planner using the chat prompt template, the chat OpenAI instance, the str output parser, and finally a dictionary with the base response. We also define the arguments for a variable using the chat prompt template, the chat OpenAI instance, and the str output parser instance. Then we define the arguments underscore against variable by using the chat prompt template, the chat OpenAI instance, and the str output parser instance. Finally, we define the final responder variable using the chat prompt template, the chat OpenAI instance, and the str output parser instance. And we also define the chain using the planner, a dictionary containing results 1, results 2, an original response, keys, and then the final responder. We then call the invoke method on the chain variable by passing a dictionary with the key input and the value scrum. This will return the following text. While Scrum has its potential cons and challenges, many organizations have successfully embraced and implemented this project management framework to great effect. The cons mentioned above can be mitigated or overcome with proper training, support, and a commitment to continuous improvement. It is also important to note that not all cons may be applicable to every organization or project. Regarding querying a SQL database with the LangChain expression language, we can replicate our SQL database chain with Runnable. We import the chat prompt template from LangChain prompts. We define our template variable and then our prompt variable using the from template method of the chat prompt template class. We import the SQL database class from LangChain utilities. Then we'll need the Chinook sample database for this example. We define the DB variable using the from URI method of the SQL database class. We define our get schema method and our run query method. Then we import the chat OpenAI, the str output parser, and the runnable pass-through classes from LangChain. We instantiate our model variable and we build our SQL response chain using runnable pass-through, the prompt, the model.bind method, and the str output parser instance. We can call the invoke method on the SQL response variable by passing the question how many employees are there, and we'll obtain as output the SQL code select count star from employee. In another example, we can simply define another template, create the prompt response variable using the from template method from the chat prompt template class. We build our full chain using the runnable pass-through, prompt underscore response, and the model. And finally, we can call the invoke method by passing the question how many employees are there, and we'll obtain an AI message object with the content there are 8 employees. Regarding agent, you can pass a runnable into an agent. You need to import the agent executor, the XML agent, and the chat anthropic classes. We define our model using the chat anthropic class by selecting model claude2. We define our search method, the tool list variable, the prompt variable using the XML agent class to get the prompt to use. Then we define the convert intermediate steps method, which contains logic for going from intermediate steps to a string to pass into model. This is pretty tight to the prompt. Then we define the convert tools method, which provides the logic for converting tools to string to go in prompt. Building an agent from a runnable usually involves a few things: data processing for the intermediate steps, the prompt itself, the model, and the output parser. Regarding data processing for the intermediate steps, these needs to be represented in a way that the language model can recognize them. They should be pretty tightly coupled to the instructions in the prompt. The model should be complete with stop tokens if needed, and the output parser should be in sync with how the prompt specifies things to be formatted. We then define our agent by first defining a dictionary with a question and intermediate steps keys, both pointing to lambda functions as their value. Then we use the vertical pipe to an invocation of the partial method of the prompt object, which then pipes into an invocation of the bind method of the model object. And finally, we have the get default out parser method invocation of the XML agent class. We instantiate our agent executor by calling the agent executor constructor and passing the agent, the tool list, the agent, and the tool list. Finally, we call the invoke method by passing the question what's the weather in New York to the agent executor, and we'll obtain the following result: entering new agent executor chain, tool search, tool input weather in New York 34 degrees, final answer the weather in New York is 34 degrees, finish chain.
If you've enjoyed this video so far, it will really help me a lot if you subscribe to my channel by clicking the subscribe button and hitting the notification bell. I know most of you are not subscribed already, so you might miss out on any future content that I will release on this channel. Please subscribe today. Thank you. I recently created a Patreon account for the data science channel. At the moment I create my videos in my spare time while also working a full-time job. Having a Patreon would allow me to receive donations from people like you who have enjoyed the videos that I've produced so far, and will help me improve the quality and the frequency of the videos that I post on the channel. Moreover, for each of the membership options available, I will provide some extra services for those of you who decide to support me. Essentially, you can pick between 3 tiers of membership. In the associate tier, you can provide me with the equivalent of a cup of coffee. I would provide you with all the materials and the code that I use during my videos, and with a monthly live session with myself where you can ask questions and we can discuss various topics related to data science. If you want to support me even further, you have the senior data scientist
enthusiast tier, where I'll also provide you with monthly one-on-one sessions with myself, where I'm going to provide you with guidance, mentorship, and answer any questions regarding your data science journey. Finally, for those of you who are more generous, you can opt for the lead data scientist tier, where I'll be happy to provide weekly one-on-one mentorship sessions, and as a bonus, I'll produce a 1-hour-long tutorial about the data science topic of your choice once you've been a member for 12 consecutive months of the lead membership. Each higher membership will contain all the benefits of the previous membership tier. So for senior data scientists, you'll also get the benefits of an associate data scientist, and for a lead data scientist, you'll also get the benefits of an associate and senior data scientist. I would definitely recommend you to consider supporting me in this journey. And the dictionary return will contain the question, what's the weather in New York? And the output, the weather in New York is 32 degrees. Regarding code writing, here's an example of how to use LangChain expression language to write Python code. We import the chat OpenAI, the chat prompt template, the str output parser, and the Python REPL classes from LangChain. We define our template, write some Python code to solve the user's problem. Return only Python code in markdown format. Example, Python. Then we define the prompt variable by calling the from messages method of the chat prompt template class. We define the model variable by instantiating the chat OpenAI object. We define the underscore sanitize output method, and then we build a chain from prompt, model, an instance of str output parser, the sanitize output method, and the run method of a Python REPL instance. We can then call the invoke method on the chain by passing the input what's 2 plus 2, and we'll get the messages Python REPL can execute arbitrary code, use with caution, and we'll also get the answer, which is 4, because 2 plus 2 equals 4. Routing by semantic similarity. Using the LangChain expression language, you can easily add custom routing logic to your chain to dynamically determine the chain logic based on user input. All you need to do is define a function that, given an input, returns a runnable. One especially useful technique is to use embeddings to route a query to the most relevant prompt. Here's a very simple example. From LangChain, we import the chat OpenAI, the OpenAI embeddings, the prompt template, the str output parser, the Runnable lambda, and the Runnable pass-through classes. We define our physics template variable and the math template variable. We define the embeddings variable as an instance of the OpenAI embeddings. Then we define the prompt templates as a list containing physics template and math template. We then define prompt embeddings by making a call to the embed documents method of the embeddings variable and passing in the prompt templates variable. Then we define the prompt router method and the chain, which contains a dictionary with a query that we then pipe to the Runnable lambda object, then to the chat OpenAI instance, and finally to the str output parser instance. We can then print the results of calling the invoke method on the chain variable and passing the what's a black hole question, and we'll get the answer. Using physics, a black hole is a region in space where gravity is extremely strong, so strong that nothing, not even light, can escape its gravitational pull. We can also call the invoke method again, but this time we're gonna ask a question that is more math related, such as what's a path integral, and we'll get the answer. Using math, thank you for your kind words. I'll do my best to break down the concept of path integral for you. In mathematics and physics, a path integral is a mathematical tool used to calculate the probability amplitude or wave function of a particle or system of particles. In LangChain expression language, you can also add memory. The following shows how to add memory to an arbitrary chain. Right now, you can use the memory classes, but need to hook it up manually. First, we do the import. From operator, import item getter. Then we import the chat OpenAI, the conversation buffer memory, the chat prompt template, the messages placeholder, the Runnable lambda, and the Runnable pass-through from LangChain. Classes from LangChain. We define our model variable as a chat OpenAI instance and our prompt variable by calling the from messages method of chat prompt template. We instantiate the conversation buffer memory object by passing return messages through, and then we call the load memory variable method on memory. We then try to build a chain from Runnable pass, which we then pipe to the prompt variable and then to the model variable. Then we define our inputs dictionary containing the input how. Hi, I'm Bob. We then call the invoke method on the chain variable and pass the inputs, and we obtain the response. The response is an AI message object with the content hello Bob. How can I assist you today? We can then call the save context method and pass the inputs and the output response.content attribute to it. And then we can call the load memory variable method on the memory variable. And we'll obtain as a result a dictionary containing a key named history and a value containing the human message hi I'm Bob and the AI message hello Bob. How can I assist you today? Then we can define the inputs variable as a dictionary containing input what's your name and call again the invoke method on the chain using the new input. And the response that we'll get will be an AI message with the content your name is Bob. We can also add moderation in the LangChain expression language. The following will show how to add moderation or other safeguards around your LLM application. We import the OpenAI moderation chain, the OpenAI, and the chat prompt template classes. We define our moderate variable by instantiating an OpenAI moderation chain instant. We define the model variable by instantiating an OpenAI instant, and the prompt variable by calling the from messages method on the chat prompt template. We build our chain from the prompt and the model. We then call the invoke method on the chain, passing the input you are stupid, which will return the message you are stupid. We can then build a moderated chain using the chain and also pipe moderate. In this case, if we call the invoke method on the moderated chain and pass the you are stupid input, the output would be text was found that violates OpenAI's content policy. You can also use tools with runnables pretty easily. For example, you can pip install DuckDuckGo search. You can import the chat OpenAI chat prompt template, DuckDuckGo search, run, and str output parser classes from LangChain. You can then instantiate your search variable as an instance of DuckDuckGo search run. You then define your template variable, your prompt variable from chat prompt template, and the model variable from chat OpenAI. You define your chain using the prompt, the model, the str output parser instance, and the search. And finally, you can call the invoke method on the chain by passing the input, "I'd like to figure out what games are tonight," and you'll obtain the answer. What sports games are on TV today and tonight? Watch and stream live sports on TV today, tonight and tomorrow. Today's 2023 sports TV schedule includes football, basketball, baseball, hockey, motorsports, soccer, and more. Watch on TV or stream online on ESPN, Fox, FS1, CBS, NBC, ABC, Peacock, Paramount Plus, Fubo TV, local channels, and many other networks. The agent's dynamically called tool. The results of those tool calls are added back to the prompt so that the agent can plan the next action. Depending on what tools are being used and how they're being called, the agent prompt can easily grow larger than the model context window. With LangChain expression language, it's easy to add custom functionality for managing the size of prompt within your chain or agent. Let's look at a simple agent example that can search Wikipedia for information. We pip install LangChain Wikipedia. We import item getter from operator. We then import agent executor, OpenAI functions, agent output parser, chat OpenAI, chat prompt template, messages placeholder, chat prompt value, Wikipedia query run, Wikipedia API formatter, classes from LangChain. We instantiate our wiki variable by creating a Wikipedia query run object and passing to it a Wikipedia API wrapper object. We then instantiate our tools list that will contain the wiki variable. We then proceed to instantiate our prompt using the from messages method of the chat prompt template class. Then we create our LLM variable by instantiating a chat OpenAI object. Let's try a many-step question without any prompt size handle. First, we create the agent variable that will hold a chain formed out of a dictionary with the keys input and agent scratchpad that is then fed into the prompt variable, then into the LLM.bind method output, and then into the OpenAI function agent output parser instance variable. We then create the agent executor variable by instantiating an agent executor object. And finally, we call the invoke method on the agent executor with the input, who is the current US president, what is their home state, and so on. Then the output is generated, entering new agent executor chain, invoking Wikipedia with list of presidents of United States. And then it goes for a series of pages until it reaches the page about Joe Biden, the current US president, on Wikipedia. Then it goes to the page presidency of Joe Biden, then family of Joe Biden, then cabinet of Joe Biden, then the page Delaware, then the page for Delaware City in Delaware, then Delaware River, then Lenape, and finally University of Delaware. And we get a response, bad request error, error code 400, message. This model's maximum contact length is 4097 tokens. However, your messages resulted in 5478 tokens. Please reduce the length of the messages or function. So unfortunately, we ran out of space in our model's context window before the agent can get to the final answer. Now let's add some prompt handling logic. To keep things simple, if our messages have too many tokens, we'll start dropping the earliest AI function message pairs. This is the model's tool invocation message and the subsequent tool output message in the chat history. We'll create a method condense prompt, then we'll create our agent chain with the dictionary, with the keys input and agent scratchpad that is then fed into the prompt variable, then into the condensed prompt variable, then into the output of the LLM bind function, and finally into the OpenAI functions agent output parser instance. Then we create the agent executor by instantiating an agent executor object, and finally we call the invoke method with the input, who is the current US president, on the agent executor variable. Once again, we go through a series of Wikipedia pages until we reach the University of Delaware page. And in this case, we have a valid response with the input, who is the current US president, and the output. The current US president is Joe Biden, his home state is Delaware, and all the additional information that we've requested.